Good morning. Last time we have dealt with Gauss 2-point rule, and we have derived what are those 2 points, Gauss 2 points on the interval -1 to 1. So let's quickly summarize the things what we have done. So what we have done is we have started with the three functions f0, f1, and f2 over the interval. So we are talking right now on the interval -1 to 1. So the f function is defined from -1 to 1 to r. It's a real valued function, and you are trying to approximate the integral -1 to 1 f of x dx by using Gaussian quadrature rule. Okay, so we want to approximate this. So how we have proceeded there? Like we were interested in finding the orthogonal polynomial, okay, and of degree 2, which is orthogonal to the polynomial of degree less than or equal to 1. So which is same as we can work with. We can take three functions, 1, x, and x square over the interval x on the -1 to 1. And then by using the Graf-Smith orthonormalization process, we can derive these three polynomials, which are such that, so these are such that if you look at the any pair gi comma gj will be behave like direct delta function. Okay, it will be 1 whenever I equals to j, and it will be 0 when I is not equals to j. And we know that these polynomials are nothing but the Legendre polynomials. Okay, so we have got the g2 which is given by this, okay, that quadratic equation, so which is orthogonal to constant polynomial as well as orthogonal to linear polynomial. Okay, so this implies that this result, so the first result g2 comma 0, this inner product is 0, implies this following. So this is x square minus 1 by 3. So see, constant you can put on the right side. So the constant doesn't matter. So you can still you can put here constant. So constant will go towards the right hand side. So constant multiple will not be given any problem here. So similarly, this g2 is also orthogonal to the linear polynomial. So which is means you can work with the function x only. Okay, since these are true, because why it is so? Because you can see this span. If you recall, span of g0, g1, and g2 is same as the span of f0, f1, f2, and which also says that so span of f0, f1, f2 means what? It's a polynomial of degree less than equals to 2, set of all polynomials of degree less than equals to 2. So if g2 is orthogonal to x and g2 is orthogonal to the constant polynomial, so it's definitely g2 is orthogonal to the linear polynomial and constant polynomial. Okay, so these are, because of this, these results hold true. Now let's choose these points as the interpolation points. So let's take the root of this quadratic polynomial g2, which are the plus minus 1 by root 3. So we can denote x0 as -1 by root 3 and x1 equals to 1 by root 3. Then what you will do, you will treat these as an interpolation points, and then you will go for writing an interpolating polynomial of degree less than equals to 1 by using these points. And then you will see there the error term will be reduced to the error term will be reduced to goes to 0 whenever you will go for polynomial of degree less than equals to 3. So how it was there is, so once you have x0 and x1 chosen, so with the help of these interpolation points, which are also called Gauss 2 points, Okay, so with this, we have considered the polynomial of degree 1, that is f of x naught plus f of x naught comma x1 x minus x naught. So this is your p1 of x, which is an interpolating polynomial by using the point x naught comma x1, and this is the error term here. Okay, so now once you integrate over this interval -1 to 1 f of x dx, so first these two terms, if you integrate, that is going to be turn out to be the f of x naught plus f of x1 that we have done several times. Okay, so I have leave it here as it is. And then what about the error? If you have is integration -1 to 1 f of x naught comma x1 comma x, and this we are also sometimes denoting as w of x. Okay, so we are also denoting, this is also for this case is w of x, because you are interpolating with the help of interpolation points x naught and x1. Now, note that this w of x, so you have chosen x naught and x1 in such a fashion, means so that this w of x is orthogonal to, so if you so you see, if you look at back, okay, then it can be easily verified that integration -1 to 1 w of x times x to the power j dx is equals to 0 for j equals to 0 and j equals to 1. This is not true for any interpolation point. This is only true for the point interpolation points, which are Gauss points. Okay, so just now if you go back and check, this will verify our what we have stated just now. Okay, this is your w of x, so w of x into 1, w of x into x, so that is going to be 0, integration over -1 to 1. So with the help of this, what we will do, so we are going to use the recurrence relation of the divided differences. Okay, like we have done for midpoint rule, like we have done for Simpson's rule. So then we have arrived with the, so if you let me here, if I just want to put some remark here, so you can say here, this is f of x naught comma x1 comma x. If I recall, that is going to be some f of some y naught x naught comma x1, okay, plus f of y naught comma x naught comma x1 comma x time x minus y naught. But you have chosen, you can choose y naught is fixed, but y naught can be chosen as x naught itself. So you, that is a one step. So then you take this w of x with this here, okay, and w of x with this here. Then if you integrate, this term is remain constant, but integration -1 to 1 w of x dx is 0. So this term will not contribute anything. Then you will use the similar recurrence over this divided difference formula. Then you will choose another point y1 that you can choose equals to x1. So x naught is repeated twice, x1 is repeated twice. Then you have x minus x naught into x minus x1 into w of x, that is going to be giving you the following integrate here. Okay, so this is in the similar way what we have derived in the case of Simpson's rule or midpoint rule. Okay, so once you have this, then because see x0 and x1 are the Gauss 2 points, they are not, we don't know where they are, so they are symmetrically placed with the they are symmetrically placed, right, with respect to the midpoint. Okay, now see we are not sure that where x minus x naught is less than 0 or x minus x1 is greater than 0. So mean value theorem may or may not be applicable here. We don't know. But in this case, once you have chosen x equals to x, means x naught, y naught equals to x naught and y1 equals to x1 in the recurrence formula, then you have, this is a square term. So the square term is always remain greater than equals to 0. And this divided difference remains continuous whenever you assume that f is 4 times differentiable and it is continuous. So then you can apply the mean value theorem, which applies the is the following. So f, this is using 4 points with x, so 5 points. So it will be, when you choose x0 and x1, they are interpolation point. So in the limiting case, they are going to tend to the fourth derivative at some point d between the interval x0 to x1 by 4 factorial. And this term now it can be easily integrated, and you can find the error term, precise error term from here. Okay, so this we have done. So what is here is and finally what you will get is error is nothing but, if you after integration, what you will get is going to be a fourth derivative at t by 135. Okay, so which straightforward tells you that the function, so in the Gaussian quadrature, so when you use the 2 points, so it is going to be exact for polynomial of degree less than and equal to 3, because fourth derivative, error has the fourth derivative. The fourth derivative of cubic polynomial is 0. So till cubic polynomial, the error is 0. For that also you can verify by taking f of x equals to 1, f of x equals to x, f of x equals to x square, and f of x equals to x cube. You can verify this formula remains exact for 1 comma x square comma x cube. That you can do from your side. Okay, so and the error term is this. We were only focused on the interval -1 to 1. Okay, now we wish to go for the formula of, for integration a to b g of x dx, f of x dx, you can say. So how would we go for it is, we are going to map the interval -1 comma 1 to the closed interval a to b, and we are going to map it in a continuous manner, and that map must be 1 onto correspondence. Okay, so mean, in other words, you are going to find a possible substitution of the function x, so that the limits will change into integration a to b. That's another way. Okay, so this is we are going to do first now, then we are going to go for the case for composite 2.1. Okay, right. So let you have g is a real valued function now defined on the closed interval a. So we can define the 1 onto map or from the interval -1 1 to AB by following the following formula. So if you want to see how it has come, is it will be, so we were interested in a map which is 1 onto, okay, and which maps -1 1 onto a to b. So we are going to go with the some straight line. Okay, so you can see that is, let's say phi of t is equals to lambda t plus some beta. So they are such that phi of -1 is equals to a, and phi of 1 is equals to b. If you substitute these if you solve these two equations in two unknowns, you will get the lambda value is b minus a by 2 and beta value is a plus b by 2. And see, this is a continuous map. Now, not only that, moreover, this is if you look at the phi dash, what is phi dash is, so b minus a by 2. And since a is less than equals to b, so this is so a is greater than, a is less than b, so this is always greater than 0. So it says that phi is an increasing function, and it is mapping from -1 to a onto a and 1 onto b. So it is continuous function, so it is continuously mapping, so it's a function continuous, and which also establishes its 1 1. Okay, and for every point AB you can find unique t, so that you can define here some c, and then you can find t for which value of c you will get, that will lie here in the -1 to 1. So that can be established by looking at the definition of phi. So phi is continuous, moreover phi is increasing, and it maps left hand point to left hand point, and right hand point onto right hand point here. Okay, so these all three things will together will show that is a 1 1 onto correspondence. So what we are going to do here in the case of this integral a to b g of x dx, we are going to substitute x equals to by this map. In linear algebra, you also known this is also known as an affine map. Okay, so if the constant term is not there, this is known as linear map. Okay, it's a linear. But if it is constant term is added with linear term, it is called as affine map, whose second derivative is 0. So here in the case for approximating this integral a to b g of x dx, you are going to substitute x equals to phi of t. So then t value lies between -1 to 1, so limit will change into -1 to 1, and dx is replaced by pi dash of t dt. Okay, so that is what we are going to do now. So we are going to replace x, substitute x equals to by this affine map p of t, then limits will transfer onto the -1 to 1, and you have the form the integrand with a function of with respect to t. Okay, right. So here it is. So we once you substitute x equals to, we have substituted. So we have made substitution. Okay, substitution. We have made a substitution x equals to phi of t. So whenever x lies between a to b, t lies between -1 to 1. So dx is equals to phi dash of t dt. Now, so this is going to be g of p of t. Phi dash of t is, just now we have seen from the previous slide that phi dash of t is b minus a by 2. Okay, so that is going to be replaced here. Phi dash of t dt is b minus a by 2 times dt. Okay, so this is a composite function g compose phi of t dt. So now this is you can treat this as f of t. Now you know the Gauss 2-point rule. Gauss 2-point rule will says that this is equals to f of -1 by root 3 plus f of 1 by root 3. So this is here, and then you can write the similar way the error term here. Okay, so let's take your questions now. So y x equals to phi of t. So this is like we have made a substitution here. We can interchange the limits to -1 to 1 for a general interval integration a to b. Okay, so phi is a 1 onto correspondence between -1 onto a to b, which is defined by this. Okay, so we have looked for an 1 onto correspondence between these two intervals because we know the Gauss 2-point formula for the interval -1 to 1 f of x dx. So we want to write approximated formula for integration for a general interval, okay, a to b. Okay, so we wish to write now general formula for integration a to b g of x dx or f of x dx. You can replace it by. Okay, so here we are going to make careful substitution of x equals to phi of t, so that whenever x lies between a to b, t lies between -1 to 1. Okay, it's like substitution, how you do the cylindrical coordinates, polar coordinates, and you are transfer the change the change of limits. Okay, and right. Okay, so now this is now we have got the Gaussian quadrature rule for the general integral a to b g of x dx is given by this formula. Now if you look at the error term, what was the error term? Was f fourth derivative at t by 135. If you recall from the previous the slide, so this was for the whenever f is defined over the interval -1 to 1. Okay, so then you have the error formula is f fourth derivative at d is some point inside the interval -1 to 1. Now, if we want to write the error formula on the interval integration a to b, so then that function integrand is going to be taken as f function, and which you are going to differentiate 4 times and substitute. Okay, so if you see, if you carefully match what is f of t, g compose phi, and now you use the chain rule, and use the fact that phi dash of t is nothing but the b minus a by 2. So 4 time derivative, you have phi dash of t come 4 times. So b minus a by 2 to the power 4 will come. Okay, then g fourth derivative of p of t. So then you just replace here a fourth derivative with d by the following formula. So once you substitute here, so you have this is going to be the error formula for all the general interval. Okay, now if you go back and check in the Simpson's rule, trapezoidal rule, or corrected trapezoidal rule, other rules what we have learned, midpoint and rectangle as well. Okay, so then you have seen that whenever you are talking about a single interval, then there you are having the error is of order h to the power 5. Okay, or h to the power 5 or h to the power 3 or h to the power 2 and so on. Okay, but whenever you are going to consider the composite rule, means you are subdividing the interval a to b into n equal subintervals, and then you are, if you are calculate the error, so then one power of h will be lost. So you can't help here as well. So one power will lost here as well. So let's look at it. So this is the summary that integration a to b f of x dx is, if instead of g I have written this f, so final formula is going to be b minus a by 2 times f of x naught plus f of x1. So then x naught and x1 are explicitly on the interval a to b, that they are going to be symmetrically placed with respect to the midpoint of the interval. Okay, so you have, this is interval a to b, and you are having a plus b by 2 here. So one point is symmetric, other point is symmetrically placed on this side. Okay, so what are those is the points are explicitly given here, and error formula is also explicit. Okay, so for the general interval Gaussian quadrature for 2 points rule, okay, that is given by this, where the Gauss 2 points are given by this formula. So let's consider the Gauss 2 point rule in a composite manner. Now you have, so let's divide the interval a to b on n equal subparts, so x0, x1, x2 and so on. Equidistant point you can take. Okay, now each interval you have to consider that affine map, because you see, if I go here, what I'm going to do is integration a to b f of x dx is going to be written as summation I equals to 0 to n minus 1 integration xi to xi plus 1 f of x dx. So that is what we have done for similarly Simpson's rule, trapezoidal rule for the composite rule. Now you are looking the Gaussian quadrature formula over this interval xi to xi plus 1. So instead of a to b. So you are going to consider the affine map over the interval this from minus 1 to 1. On the interval minus 1 comma 1. Okay, so this is what is happening here. So so that is given by, so previously what was defined as a plus b by 2 plus t time b minus a by 2. So if you look at the if you recall from the previous slide, that p of t was given by b minus a by 2 plus t time a plus this is a plus b by 2 plus t time b minus a by 2. Okay, so that can be generalized over the interval xi to xi plus 1. So instead of a and b, now you are going to use as xi and xi plus 1 respectively. So then you will get the all the possible affinements. So there are n subintervals. So you have here I is equals to 1, I is equals to 0, 1 and so on, n minus 1. So I is starting from 0 and ending with n minus 1, because here is xi plus 1. We are ending with the point xi plus 1. Now, and the respective Gauss 2 points on the interval xi to xi plus 1 is, if you recall, what was those Gauss points? Midpoint a plus b by 2, so xi plus 1 by 2 minus 1 by root 3 time b minus a. What is b minus a? Is the length of the interval, that is xi plus 1 minus xi. but that is equidistant, and that is equals to h for the composite rule. So it is going to be h by 2 for any I. Okay, so because they are equidistant, so that is going to be h by 2 root 3. So similarly for the phi I at 1 by root 3, similarly for phi I minus 1 by root 3, and I is running from this. So once you have all this now here, then you can certainly write point composite rule. So h by 2 is sitting, you have here, if you recall, what was the formula for integration a to b f of x dx was, you have, that is going to be b minus a by 2 f at x naught plus f at x1, if you recall from the previous slides. So this interval xi plus 1 minus xi divided by 2. So instead of a and b, you are going to use the xi plus 1 minus xi. So xi plus 1 minus xi is again h, but h is same for every I. So h by 2 is out. Then these x0 and x1 are the Gauss 2 points inside the interval a to b. So similarly, these Gauss 2 points are given by, on the interval is phi I at minus 1 by root 3 and phi I at 1 by root 3. And similarly, you can calculate the error as well. So for each interval you have, so if I recall, what was the error on the interval a to b? Okay, so what was error on, you have a to b was a fourth derivative at d by 135, if you recall from the previous slide. Now see, now you are talking about the interval xi to xi plus 1. So where here d lies between, so once here I have forgotten to take b minus a by 2 to the power 5. I recall. Okay, this is fine. Now see, now if you take the interval xi to xi plus 1, then you have xi plus 1 minus xi by 2. So that is h by 2 to the power 5. F fourth derivative at some di divided by 135. Okay, so this is what had happened here. So that, and then you have to run summation over I. Okay, so now this h by 2 to the power 5 is constant, 1 by 35 is 1 by 135 is constant. Then that is going to be h by 2 to the power 5 times 1 by 135. Now, like we have done for the case of Simpson's rule or other rules, so this summation I equals to 0 to n minus 1 f fourth derivative at di can be replaced by n into f fourth derivative at some point eta. Okay, that we have already seen. This is, it is required the continuity of the fourth derivative. Okay, right. So once you have this, okay, so then n into, so n into what is h is b minus a by n. So one h will get clubbed here, so n will get cancelled from there. So b minus a is sitting here because of one h is observed here. So b minus a by n. Okay, and 1 by 2 times 135 is 1 by 270. So n will get cancelled here, and you remain with h by 2 to the power 2. Okay, so with this, so let's put in the comparison table for with the other rules. Okay, and see how many number of function evaluations are required for Gauss 2.0. Okay, and so it is very clear from here that the this Gauss 2-point rule, composite rule, is going to be of h to the power 4. So this is same as Simpson's rule, and it also requires the smoothness is fourth derivative exists. So C4 smoothness is also required. And how many number of function evaluation is required in the for the Gauss 2-point rule is, so in each, so you have subdivided into n equal subparts, right? So you have subdivided a equals to a to b. If I write, this is union of I equals to 0 to n minus 1 xi to xi plus 1. Right, you have take the part, you have taken the partition of AB with equidistant point, and these are distinct intervals. Okay, and then moreover, each point will have two Gauss points, right? So there are n sub-intervals. Okay, so there are two n Gauss points. So each interval have 2 points. So there are n sub-intervals. Each will contribute 2, 2, 2. So that will be 2 times n. So 2n Gauss points will be observed from here. Okay, and then you have to calculate, or you have to evaluate the function value at those points. So total number of function evaluation is 2n. Okay, so the number of function evaluation is 2n. So what we have is, so sum is Gauss 2 point. Then we require the smoothness is C4. It is order of convergence is OH to the power 4. Number of function evaluation is 2n. Just now we have counted. And it is going to be exact for polynomial of degree less than equals to 3. But here what we have done is only we have used the degree of interpolating polynomial was 1. And in the Simpsons it was 2. Corrected trapezoidal rule it was 3. So all these are, so except this. So here the number of function evaluation is n plus 3 and here is 2n and here is 2n plus 1. So Simpsons and Gauss 2 point. As n large, 2n and 2n plus 1 are not much differ. Okay, so they are at the same path. Okay, so there's not much difference because of the number of function evaluation, order of convergence, smoothness required. Okay, so only corrected trapezoidal rule is evaluating, it requires number of function evaluations are n plus 3. But here one condition was that you require the values at f dash at a and f dash at b. Okay, additionally you require the information that derivative value. Okay, so but this will not, see, this is same as Simpsons, so this behaves like Simpsons rule. But this, so at this fine, it means whether you use Simpsons rule or whether you use Gauss 2 point rule, doesn't matter. Okay, so what will happen if you increase the degree of the polynomial? Okay, means we are, instead of 1, we are going to increase degree of interpolating polynomial is 2, 3. Or in other words, if you consider the Gauss 3 points, 4 points, 5 points, and so on. See, we are increasing the degree of interpolating polynomial. Keep in mind that we are not going for composite rule. We are only extracting 3 points from the interval a to b or 4 points from the interval a to b. Those are called Gauss points. Okay, so we are not going for composite rule. We are only extracting the n points or k points, Gauss k points. So the situation will be very good here whenever you are going to go for Gaussian quadrature rule for more points, means like 3 points, 5 points, 6 points, and so on. Okay, so now we are going to generalize the Gaussian integration formula, okay, in the next step now. Okay, so let me take your questions here, so if you have any. Okay, so the questions. Okay, so let's look at the Gauss n plus 1 point rule. So like we have done the for Gauss 2 point rule, we have constructed a sequence or constructed a set of functions which are orthonormal, means the pairwise, if you take any two, their inner product is 0, different one, and if you take the same one, that their inner product with itself is going to be 1. Okay, so we are going to apply the similar process here, and we are going to extend in the same fashion. So let's consider x equals to the CAB, and where inner product is defined as the following integration a to b f of x times c of x dx, and 2 norm which we have denoted by square root of the inner product of f with itself. Now, so for Gauss n plus 1 point rule, so Gauss 2 point rule, we have considered 1x x square. Okay, so for Gauss n plus 1 point rule, what we require is f1 x x square x cube and so on till x to the power n plus 1. Okay, so these polynomials From there we are going to get the orthonormalized polynomials, which are also called known as Legendre polynomials. Okay, so which can be obtained by using the Gram-Schmidt orthonormalization process. Okay, so this is the general scenario. So 0 of x is nothing but f0 by this two norm f0, and we have, so you can recall the Gram-Schmidt orthonormalization. So then Rn is defined by Fn minus, you are going to remove the component of Fn in the direction of G0, G1, G2 and so on till Gn minus 1. Okay, so we are going to remove the component in the direction of them, and then this polynomial, so this Rn is going to be is a polynomial of degree n. Okay, and then it can be shown that this Rn is orthogonal to G0, G1, G2, Gn minus 1. It also can be drawn like we have done for Gauss point. Okay, and then this that nth degree polynomial, that Legendre polynomial, you can say, is going to be defined by Rn of x divided by its norm. Okay, so like earlier, span of G0, G1, G2 is same as span of F0, F1, F2. So similarly, span of G0 to Gn is also same as span of F0 to Fn. Means, see, you must have seen in during the session for Legendre polynomials, okay, that you can represent every polynomial in the form in the linear span of in the span of the Legendre polynomial as well. It's a vice versa. So from the from you can always write summation of ai pn of x. Okay, every polynomial you can write in the form in the unique way. Okay, similarly, from the, if you have the representation in the form of Legendre polynomials, you can simplify them and you can find the corresponding polynomial of degree n. Okay, so these spanning sets, both spanning sets are same. What is important here is these polynomials has n distinct, so this n, if you consider Gn of x, okay, so they have distinct n real roots. Okay, so that is what the very important thing here. So if you and the root of this equation and root of these polynomials are called the Gauss points. Okay, so this is what the idea we have used for Gauss 2 point as well. Okay, and this Gn is orthogonal to any polynomial of degree less than equal to n minus 1. Okay, that also we have in the same in that manner only we have constructed. So Gram-Schmidt orthonormalization process gives the guarantee that Gn of x is going to be orthogonal to G0 to Gn minus 1, or in other words is going to be orthogonal to 1 x and so on x to the power n minus 1, or any polynomial of degree less than equals to n minus 1. Okay, right. Now, so G0, G1, G2, Gn are known as Legendre's polynomial. Second thing is Gn polynomial. Gn is a polynomial of degree n. So fundamental theorem of algebra says that it has exactly n roots, but since they are orthonormal, okay, and they are Legendre polynomial, they has n distinct real roots. So we say x0, x1, x2, xn minus 1 if you start with x0, because n roots are there, so till xn minus 1 are the n Gauss points. Further, if you take any two pairs of these Legendre polynomials, they behave like direct delta function. So whenever I equals to j, the norm is 1. Whenever I not equals to j, they are orthogonal to each other. Okay, and so because we are going to identify the x0 to xn, okay, so we have considered here gn plus 1 is going to be orthogonal to g0 to gn. Okay, so like the fashion we have constructed gn, similarly you can construct the gn plus 1 by redefining the Rn plus 1 by Fn plus 1 here, replacing n by n plus 1. Okay, on the right side. Okay, that you can get it from here in the same. Now these, so similar concept is span of G0 to Gn can be shown as span of 1 to x to the power n. And also, like I have told, so once it is true, so Gn plus 1 is orthogonal to any polynomial of degree less than equals to n. So then, and also this is a Legendre polynomial, it has n distinct real roots. So let's say they are x0, x1, x2, xn. So you can factorize them in Gn plus 1 as the follows. So alpha n plus 1 is some constant. So this is constant. And these are factors. So x0, x1, x2, xn, these are called Gauss points. And just now we have seen that Gn plus 1 is orthogonal to all any polynomial of degree less than equals to n. So this is your Gn plus 1. If you multiply by alpha n plus 1 here, okay, you multiply by alpha n plus 1 and divide by alpha n plus 1. So this alpha n plus 1 together with you Gn plus 1 is going to be orthogonal to x, x square, x cube, and constant, and so on till x to the power n. So this will tells you that this is the similar thing as like this. Okay, this can be derived from here straightforward by substituting a0 equal to 1. Okay, or you can substitute aj equals to 1 and rest of the coefficients a0 to an, other means not equals to j, are 0. Then you will get the following property of the Gn plus 1. So if you use this, then we are going to define the now Gaussian quadrature rule. Okay, so these x0, x1, x2, xn are called Gauss points. So using these n plus 1 points, we are going to write interpolating polynomial of degree less than equals to n. Okay, because n plus 1 points will lead to interpolating polynomial of degree less than equals to n. So that is going to be that you can write in the form of Lagrange representation, or you can go for Newton's. So we have considered here Lagrange representation. This is the interpolating condition. This is an interpolating condition that Pn of xj is equals to f at xj. This is an interpolating condition that we have already seen. Now, what we have important is the error term. What is the error? Is the divided difference into w of x. What is w of x? Is product of x minus xi. Now, note that we have chosen x0 to xn are Gauss points, and they are such that, so we just, yes, if you see, this is nothing but a w of x. This is red underline. Time x to the power j dx is 0. Okay, so similar, so such that Gauss points, and therefore they are such that this result hold true. So what we are going to do, we are going to use the similar technique what we have used in the Gauss 2-point rule or Simpson's rule or midpoint rule. You are replacing the divided difference by using the recurrence formula. Then there what we have done, so x0 repeated twice, x1 repeated twice, and so on, xn repeated twice, you will get a w square, and rest of the things will get cancelled because of this property. Okay, so here we are now. So we have this following error formula. So what we are going to do is f of x0 to xn comma x can be replaced by the recurrence relation. So by using recurrence relation, the following. So f of x0, x1 to xn plus f of, so it was here y0. Okay, that we have chosen as x0 here. So x0, and x1 to xn comma x minus x0, y0. Right now, then again you will replace this by recurrence relation that will lead to this x minus x0 into x. Then you have x1 is repeated twice. So when you go further, so if you keep on continuing this, Okay, because so the previous term will consist of x minus x naught to x minus xn minus 1. If you consider the previous term here, plus f of, you have x naught, x0, x1, x1, and so x2, and so on, xn minus 1 comma xn minus 1 comma xn time you have x minus x0 to x minus x1 and so on till x minus xn minus 1. Okay, right. So then the last term is going to be this. Now, if you multiply it by w of x and then perform the integration. So integration w of x, integration a to b, w of x dx is 0. Integration a to b, w of x time x minus x naught. Okay, then if you open it up, what is that? Is integration a to b, w of x time x. So if I want to make it clear, so let's say, so you have integration a to b, w of x dx is 0. Because x naught, x1, x2, xn are cost points. Similarly, integration a to b, w of x time x minus x naught dx is equals to integration a to b, w of x time x dx minus integration a to b, w of x time x naught is out, dx. Now both integral is 0 because w of x time x to the power j is 0 whenever j is 0 to n. Okay, so both the integral is 0, so that turns out to be 0. So you can proceed in the same manner, integration a to b, w of x time x minus x naught to x minus x1 dx. So you can open quadratic polynomial. What you will get is something like a1 integration a to b, w of x time x square. So x square coefficient is 1 only, so dx plus some coefficient a1 integration a to b, w of x time x dx plus some constant term time integration a to b, w of x dx. But you know that w of x time x to the power j is equals to dx is 0, integration is 0 whenever j is lies between 0 to n. So okay, so this first integral is 0, second term also integral is 0, third integral is also 0, so it turns out to be 0, and so on. Okay, so if you use these results here, so what you will get is only the surviving term is the last term. Okay, where you are ending with this x and you have each term will be squared now, x minus x naught square, x minus x1 square, x minus x2 square, and so on till x minus xn square. Okay, now since this does not change the sign over the interval a to b, and let's assume that, see, there are 2n plus 2, there are 2n plus 2 points. Okay, so x naught x repeated twice, x1 repeated twice, and so on, xn repeated twice. So there are 2n plus 2 points. These are 2n plus 2 points. Okay, so you require the function to be 2n plus 2 times continuously differentiable. Then this divided difference will converge to f2n plus 2th derivative at some c divided by 2n plus 2 factorial. And then the remaining integral term is integration a to b, w of x square dx. So you can apply the mean value theorem for integral. Now you can precisely integrate this term. So x minus x naught, so you know how to integrate a polynomial. And you can get the precise form of the error term. Okay, right. So instead of we are not going to evaluate the precise form of it, but we are going to show that this is a bounded one. Okay, so what we are going to have is, so if you look at the magnitude of this, so error term magnitude is equals to magnitude of this, so that the similar thing, so this is w of x whole square. Now see, x minus x naught, x minus x1, x minus xn all are bounded by b minus a. So b minus a square, b minus a square, b minus a square, and so on. How much time is that? Is going to be n plus 1 time. So that is bn minus a to the power 2n plus 2. Okay, and one more b minus a will come by evaluating the integral. So you will have, this is b minus a to the power 2n plus 3. Okay, time, this 1 by 2n plus 2 factorial is some constant c, and this is can be bounded by its maximum norm. So what it tells is the error in maximum norm is bounded. Okay, it's not blows up. Okay, it remains bounded. Okay, it cannot go beyond this. Okay, right. So however, again, you can simply integrate this term and you can get the actual error term in the Gaussian quadrature rule. Okay, so this is the Gauss n point and or n plus 1 point formula. Now what we are going to look at is, now in the next case is, we are going to look at the convergence of this Gaussian quadrature rule. Okay, so whether the quadrature rule what we have derived, okay, just now, whether it is going to be converged to the integration a to b f of x dx or not in the infinity norm. Okay, so that is our next topic. So far, if you have any doubt, you can ask me. Okay, now see, like we have seen in rectangle rule, if you recall the Riemann integral. Okay, the convergence of that rule can be observed by just imposing the condition that f is continuous over the closed interval a to b. Then that quadrature rule, rectangle rule, converges to the integral a to b f of x dx. Similarly, for the trapezoidal rule as well, it can be written as a 1 by 2 of sum of two Riemann sum, and that in the limiting sense that also the continuity of f will guarantee the convergence of the trapezoidal rule. And you can generalize this to Simpson's rule and corrected trapezoidal rule and so on. So so whether it is true for the Gaussian quadrature also or not. See, whenever we are going to interpolate a function by choosing an interpolating point or n plus 1 interpolating point, so you are very well aware about the result that there, no matter what interpolation points you choose, there always exists a continuous function, so that that interpolating polynomial does not converge to the given function f in maximum norm. Okay, that you have seen like Runge phenomena if you have look at. Okay, so similarly here, but in the case of Gaussian quadrature rule, okay, that numerical quadrature, what you have, suppose you are going to integrate the interpolating polynomial, then it is going to be converged. Okay, for every continuous function. So numerical quadrature rule for Gaussian that we have derived for Gaussian quadrature as a Gaussian quadrature rule, that is going to be converged once you assume that f is continuous. Numerical formula, but Pn may or may not be converging towards f in infinity norm. Okay, so this is going to be, we are going to show now. So this is what I've told now, convergence of Gaussian quadrature. So let x0, x1, x2, xn be Gauss points. Okay, and f of x is approximated by interpolating polynomial which interpolates f at these Gauss points. And we have considered the Lagrange form of. Okay, right. So as I stated, no matter what interpolation points you choose, there always exists a continuous function f for which the interpolating polynomial does not converge to f in maximum. Okay, right. So what can happen? So it can happen that the interpolating polynomial may or may not converge to f in a maximum norm, whereas integration a to b, that numerical quadrature, does converge to the this integration a to b f of x dx. So this is what happens in Gaussian quadrature formula, but it is not going to happen in Newton's Cotes formula that we are going to conclude at the end, why it is not happening in Newton's Cotes formula. Okay, right. Now, so for establishing the Gaussian integration, the convergence of Gaussian integration, what we are going to show that this integration a to b Pn of x dx converges to integration a to b f of x dx in infinity. Okay, as n tends to infinity. So we are going to use the following facts. Okay, the very first fact which needs to prove that wi greater than 0 for every I equals to 0 to n. So in Gaussian quadrature rule, the weights which we are going to say these are w0, w1, w2, wn, and so on. They are called as known as weights over the function f at interpolating point xi. Okay, they always are going to be strictly greater than 0. Okay, so that we are going to first prove that in Gaussian quadrature, the weights are always going to be greater than 0. And then we are going to use the fact of Weierstrass approximation theorem, which tells that every continuous function can be approximated by a polynomial. Okay, so there are two things. So the second thing we can use the directly, that Weierstrass approximation theorem. The first thing is needs to be proved. Okay, now if I want to mention here about the Newton-Cotes formula, there are also summation wi. Okay, f of xi. Wi is integration a to b f li of x dx, if you recall, for the Newton-Cotes formula. But there is what happened is they are of mixed sign. So for some at some point x naught or at some point xj, wj is negative, and other point it is positive. Okay, so this thing is not happening with Gaussian integration. So that is the advantage here in Gaussian integration, that all wi's are having the same sign, and that is nothing but the greater than 0. Okay, so this is what the difference in Cotes formula. So you have seen corrected trapezoidal rule as well. There are also weights are with minus sign in the first derivative if you look at it. Okay, so and if you go for higher quadrature, for n equals to 2 or n equals to 3, n equals to 4, and so on. Other rules, if you consider for Newton-Cotes formula, you will start with getting with the wi of mixed sign. Maybe some of them are positive, some of them are negative. Okay, so this is what the problem here is. Okay, right. So we are going to now establish the fact that wi is strictly greater than 0. Okay, right. Now if you so not that here x0 to xn are Gauss points we are choosing. Okay, right. Now so note that wi is nothing but integration a to b li of x dx, if we recall from the fact that, okay, because we have Pn of x is summation f of xi time li of x dx, li of x, and then if you perform the integration, that wi will come out like this. Now you must have seen in your tutorial sheet there was one problem that if you sum up all the cardinal functions, the sum will be equals to 1. Okay, so I can write li of x as li of x into 1. Okay, so li of x into 1. So I can replace this 1 by the following sum. Summation j equals to 0 to n lj of x. Okay, now you see this is a finite sum. You can take it outside of this interval. Okay, so I kept the first term. I have taken only the ith term here. When you put summation j equals to 0 to n li of x times lj of x dx. So whenever I equals to j, li square x dx, and whenever j is not equals to I, these are here. Now if I claim that if we claim that this integral value is 0, then this so the remaining term is this, and since these are Gauss points, x0, x2, xn are Gauss points, so this always strictly greater than 0, so integral also strictly greater than 0. Okay, so our claim will be proven once we establish the result that integration a to b li of x times lj of x dx is 0 whenever I is not equals to j. Okay, so now to prove that wi is greater than 0, now we need to show that this is equals to 0 whenever I is not equals to j. Okay, so this can be proven by using the fact that by using the orthogonality of w. Okay, by using the orthogonality of w on the functions 1 to x to the power n minus 1, right? Okay, so now for I is not equals to j, so li of x times lj of x, I have written this. Okay, so I for li of x, so it will be x minus xk divided by xi minus xk, where I is not equals to k and k is running from 0 to n. If you recall from the definition, I have written li of x explicitly here. Similarly, lj of x minus xm divided by xj minus xm. Whenever m is not equals to j, that is going to be lj of x. Now, see this term, so x minus x naught to x minus xi minus 1, and then xi plus x minus xi plus 1 to x minus xm. So x minus xi term is missing here. So x minus xi, I will borrow from this term. Okay, so from this factor, from this term, I will borrow the ith term, you can say x minus xi by xj minus xi. That I am going to extract from here. So what is here is x minus x naught to x minus xn, divide by this product of the denominator xi minus xk, where k equals to 0 to n, k is not equals to I for this one, into xj minus xi for m equals to I. And what is remaining now is product of m equals to 0 to n. M is not equals to j and m is also not equals to I. So how many factors are here? Total factors are now n minus 1. Earlier n to n were n factors, because one of the term is deleted, 0 to n, m not equals to j. Now we have extracted one on the in the this first term, product term, we have consumed here in this here. So here is remaining is n minus 1, x minus x1, x minus x2, and so on, x minus xn. Only m not equals to j and m not equals to I. So n plus 1 minus 2 is n minus 1. So this will lead to n minus 1 degree polynomial. Okay, this will lead to n minus 1 degree polynomial. And if you look at the numerator here, what is the numerator is w of x. Okay, and this the denominator is nothing but the constant, some constant value. Okay, so w of x by c times r n minus 1 of x, which is polynomial of degree n minus. Now you can now very easily see that y integration a to b, if you perform integration over here dx, why it is going to be 0, because w of x is orthogonal to polynomial of degree less than and equal to n. Okay, so it is going to be orthogonal to any polynomial of degree less than equals to n minus 1 as well. So that establishes our proof that integration a to b li of x times lj of x dx is 0 whenever I is not equals to j. Okay, so for I not equals to j, you have the 0. So wi is integration a to b li square of x dx, which is strictly greater than 0 due to the fact that x naught to xn are Gauss points. Okay, so we have established the proof. Now see these things, so this thing will not be true for any randomly chosen interpolating points. Okay, it's only true for Gauss points. Okay, because the fact that w of x is orthogonal to polynomial of degree less than equals to n. Okay, so we have established our first claim that all the weights in the Gaussian quadrature is strictly greater than 0. Okay, right. Now we are coming to the proof of the convergence of Gaussian integration finally. Now not that wi will change with respect to if you increase the number of points n. Okay, wi will be changing when you change the number of Gauss points. So it will be implicitly depending on n. So we are going to write clearly the dependence of wi on n explicitly now in the further results. Okay. Similarly, the Gauss points also will change when you increase the value of n, or when you decrease the value of n change, the Gauss points will change. Okay. So we have the dependence of wi and xi's on n. So we are explicitly writing that their dependence on n. So that's why here f belongs to C of AB. Let's say continuous function. Then we denote that in of f. What is in of f? Is the quadrature rule, that summation I equals to 0 to n wi f of xi. Now explicit dependence on n is given by this. This is not right. This is not another thing. It's only symbolized for showing the dependence of wi and xi on n. Okay. And now note that this integral formula f of x dx is exact for polynomial of degree less than equals to 2n plus 1 when you consider Gauss endpoints. Okay, so here Gauss n plus 1 points. Okay, so here summation I equals to 0 to n, so that is going to be exact, right? So this is equals to in of f. Also, if so, this is exact for all polynomial of degree less than equals to 2n plus 1. So therefore, it is also exact for f of x is constant polynomial. But in particular, you can put f of x equals to 1. This is also for f of x equals to 1. So when you substitute f of x equals to 1, that will straightforward lead you to the following result, that wi summation of weights is nothing but the length of the interval, that is b minus a. Okay, so that we are going to also use. Okay, and also we are going to use the fact that wi of n are non-negative, or you can say strictly positive. Okay, greater than 0 for any n. Okay, so now we are going to show that in of f converges to integration a to b f of x dx whenever n tends to infinity. Okay, right. Now, see, fix epsilon bigger than 0. Since f is a continuous function, therefore there exists a polynomial of degree less than equals to m such that this happens. This is because due to Weierstrass approximation theorem. Okay, Weierstrass approximation theorem. So Weierstrass approximation theorem given that for a fixed epsilon bigger than 0, for a given epsilon bigger than 0, you will be always able to find a polynomial of degree, a polynomial such that this happens. So polynomial of some degree, that is, let's say, less than equals to 12. Okay. Now note that integration a to b. So I am calculating in of Rm. You can see. See, whenever the degree is less than equals to 2n plus 1, this is going to be exact. So this in of Rm will give you the integration a to b Rm of x. When m is greater than 2n plus 1, we don't know. Okay, or there will be error. Okay, so this is what here. So we also note that in of Rm is equals to integration a to b Rm of x whenever m is less than equals to 2n plus 1, because the formula is exact for polynomial of degree less than equals to 2n plus 1. Okay, right. Now, so by observing this, now we are in the ready for the taking the magnitude of the difference integration a to b f of x dx minus in of x. Now you add and subtract in of Rm. Use the triangle inequality. This is less than equals to. Okay, that is going to be this one. See, this one remains true. This one is true whenever m is less than equals to 2n plus 1. So we are doing for m is less than equals to 2n plus 1, or you can write n is greater than equals to m minus 1, right? So it is equivalent to say that m is less than equals to 2n plus 1. So this will be exact. In of Rm will be exact for m less than equals to 2n plus 1. So what we are doing here is for m less than equal. So that is going to be, so this is going to be bounded. So integrand is bounded by the norm. In maximum norms, you are taking the maximum over the interval x to a to b. That will give you the maximum norm time b minus a, that is the length of the interval, plus this also can be taken out from the summation by taking the maximum norm time summation of j equals to 0 to n wj of n. What is that sum is b minus a. Okay, now both the things, so both coefficients norm f minus rm, the coefficients, they are infinity, and they are, you know, that is less than epsilon for m is less than equals to 2n plus 1. So that is, in the sum is 2 epsilon time b minus a, and that's it. What we have done, that will establish our claim, because if I recall the definition of convergence of a sequence, then you note that if you recall that for epsilon bigger than 0, there exists a k epsilon in natural number such that mod of xn minus x is less than epsilon for all n greater than equals to k epsilon. Now if you compare, then limit of xn is x. So if you compare this definition of limit with the previous result, so k epsilon is nothing but that m minus 1 by 2. Okay, and x is nothing but integration a to b f of x dx, and xn is nothing but in of f. Okay, so you have started with a given epsilon bigger than 0, so you can now make it arbitrarily chosen. And you can certainly find a stage afterwards that will lies in the neighborhood of in of f. Okay, so by following this will establish the convergence of Gaussian integration just by assuming that f is continuous function. Okay, right. Now, what was the problem? We have extracted from the Newton-Cotes formula that wj's could be of mixed sign. Okay, they may be greater than 0 somewhere, they may be less than 0 somewhere. Okay, so they are of mixed sign, but their summation is still b minus a, because the formula, if you look at, okay, so let's see what is happening in Newton-Cotes formula. So let's x0, x1, x2, xn are equidistant points. They have been chosen where h is equals to b minus a by m, and xi is a plus ih. So here again we are letting this superscript n by showing the dependence on n. I equals to 0 to n, x0 is a and xn is b. Now what was Pn of x? Was summation I equals to 0 to n li of x times f of xi. So this also superscript here is showing the dependence on n. Now if you perform the integral here a to b, that is going to be summation I equals to 0 to n wi of n f of xin, which is exact for polynomial of degree less than equals to n, which we have denoted by in of f. Now see, this is polynomial of degree less than equals to n, it's exact. So it is also exact for polynomial of degree 0 degree, means constant. So if you say place f of x equals to 1, then you have to also claim that summation I equals to 0 to n win f of xi is 1 for all I. So you will have the summation wi is b minus a. Still the summation is remain the same as in the Gauss point. Okay, right. So what is happening here is, so let epsilon bigger than 0 and f is a continuous function. Okay, then the Weierstrass approximation theorem gives the guarantee that there exists a polynomial Rm of degree less than equals to m, satisfying this. Okay, and this integration a to b Rm of x dx is remain exact whenever m is less than equals to n, because we know that the Newton-Cotes formula is exact for polynomial of degree less than equals to n. Now start with the similar fashion, add and subtract Rm, and then use the inequality. Okay, now this can be out by norm of f minus rn infinity. Okay, so we can integration a to b f of x minus rm f x dx. Then you use again triangle inequality. You know that mod of integration f dx is less than equals to integration mod f dx. Okay, plus this mod triangle inequality. So what it gives is less than equals to this, and the first integral that less than equals to this, and the second integral term, if you look at in rm minus in of f. So in of rm is summation wi rm of xj. Okay, now wj are not of same sign, so that is why here mod is sitting. Okay, so this is why mod is sitting still, because we don't know whether they all are positive or they are negative. Okay, so so you have this. So now you can still take this norm of f minus rm, infinity norm. You can bound this magnitude by the infinity norm of f minus rm. So this is going to be norm f minus rm, infinity norm b minus a, plus this is infinity norm. It is taken out, summation j equals to 0 to n mod of wgm. Now see, here this will not be bounded. This term will not be bounded, since we were knowing summation wjn is b minus a. Okay, we know that summation wjn is b minus a, but they are of mixed sign. Okay, now when you have mod here, okay, that is going to be unbounded. Okay, that will increase with respect to n. Okay, so this is why this term will not remain bounded, and therefore this formula will not going to converge for okay. So this is what the problem here in Newton-Cotes formula. Okay, for if you go for n higher degree. So that is why here instead of 2 point, 3.4 points, what you are going to do is you are going to you are going for composite rules, means subdividing the interval and then applying the rules there. Okay, but in the Gaussian quadrature rule, you can straightforward extract the Gauss points, n point Gauss n points, and apply. Then you will get the exactness till 2n plus 1 degree polynomial. Okay, right. So if you have any doubt, you ask. Okay.